get started. So thank you all for being here today and welcome to this latest seminar of our Frontiers in Scientific Machine Learning seminar series. So today we are very pleased to have with us Dr. Julie Bessac from the National Renewable Energy Laboratory to give us a talk on some of her work for statistical learning, model correction, and application of neural networks to super resolution. So Julie Bessac received her PhD degree in 2014 in applied mathematics from the University of Rennes, France. Between 2014 and 2023, she was a postdoctoral appointee and a research scientist in the Mathematics and Computer Science Division of Argonne National Labs. She joined the National Renewable Energy Laboratory in 2023 as a computational statistician, and she is also currently an adjunct professor in the Department of Statistics at Virginia Tech University. Her research focuses on statistical and machine learning methods for modeling, forecasting, and uncertainty quantification for very diverse applications. These include geophysical processes and their applications to energy systems, computer science, and nuclear physics. And we are very happy to have you with us today, Julie, and please take it away. Yeah.
Thanks very much. So thank you, Aniket and Sohail, to organize, for having me here and for organizing the seminar. I'm very happy to meet you. So like you said, Aniket, I will discuss two topics. Most of my work is really at the intersection between statistics and machine learning. I really like both, and I feel like they also can marry very well. So I like the idea to try to push the methodology, those two methodologies together. The first topic I will discuss is about summary statistics for physics-based model output and their correction that is observational based. I will give much more details. And then the second topic, I want to discuss how to create probabilistic outputs from neural networks. And I'll show an application in super resolution of wind fields. And so the first work is really most of the big heavy weightlifting is done by Atlanta, who you know quite well. So I think I don't need to go back to my background. You described it very well. So at the moment, I'm a remote employee for the National Renewable Energy Lab. It's located in Colorado, but I'm located actually in Virginia Tech in Virginia. And prior to that, I was at Argonne and prior in France to study. So let me tell you about my research interest quickly. Do you actually, is the zoom bar actually just like masking part of the slide, or is it not?
It's not actually.
It's not. Okay, perfect. Okay, that's good then. So most of my interests have started in spatial temporal statistics, and then I branched out to machine learning recently, deep learning. I was also interested in non-stationary techniques like regime switching models, and that also include doing a bunch of clustering, for instance. And in terms of application of the statistical methods, as most statisticians, what we're interested in prediction and also stochastic emulation and surrogate. This was actually the main purpose of my PhD, building like what we call stochastic weather generator that are basically statistical model that aimed at simulating very cheaply realistic weather condition. And in my case, it was wind speed. So yeah, like I said, some of the application I'm interested in surrogating, but also post-processing physics-based model output. And that's what I will discuss actually on the first topic, because those physics-based models typically have errors due to various factors, and statistics are very ideal tools also to take care of that. So like I said, I've also been interested in non-stationary statistics. When statistics are changing in space or in time, those have been most of my interest in that field. And then more recently, I've been interested also is fine scale statistics and super resolution. So those go together, and definitely in super resolution, machine learning has been really helpful. But each time I've been trying to add some statistics flavor to it as much as we could. And that is one topic that the second topic I will discuss today. And yeah, another application that I really enjoyed also for the past years was data compression. It turns out that there is a lot of statistical behind it, and also lots of data analysis and generation. So it's a very nice field for data enthusiasts. Okay, so some of the challenges, technical challenges that I typically face in the work that I do is the nature of the data. Oftentimes we have data of various nature. It can be, sometimes they have to be positive, like wind speed, categorical, could be like weather regimes, they have to be integers, or sometimes you have circular data like wind direction. And so each time we need to build statistical and mathematical models that can handle those features. And added to that, we have to deal with the amount of data. So sometimes it's too little data, and sometimes it's too much data. And each of these have definitely different associated drawbacks and advantages. And where also we spend a lot of time working in statistical modeling is really trying to capture the complex patterns and dependencies, right? So spatial temporal patterns, interaction between variables, especially, for instance, when you think of weather and climate, there's definitely a lot of interaction there. Scales also interact, so large scales and fine scale, they interact. And non-stationarity is a big issue. Rare events, we don't observe them very often, but we still want to model them. So that's definitely a statistical challenge. And then most of the sources of data that we have, whether it's measurement, physics-based models, they carry all sorts of uncertainty and errors that are also of different nature. And so all of those, typically we try to account for all of those features into the models that we build. Okay, and so let me start now then discussing the first work I wanted to present. So this is the work that really Atlanta carried a lot, I mean, mainly. And so yeah, it's called the Summary Statistics of Physics-Based Model Output and their observation corrected output. There's a lot of output. But so let me tell you what we intend to do here. So physics-based model output, like weather models, for instance, they have the advantages to be regularly available in space and time. They also carry a lot of physics information, especially at large scale. So that's very rich. But they are definitely subject to modeling choices and a bunch of approximations and uncertainty. So there's numerical errors, but also sometimes we still don't know how to express some of the physics that are part of them. So they are great, but they are imperfect, like everything else. And then on the other side, we also have measurements data. They are free from all of these numerical and modeling assumptions, but they can carry measurement error. Sometimes people displace actually sensors and they don't recalibrate. Sometimes you have a building built just in front of an anemometer, so that's a huge lack of information. And so what we want to do here is combine actually those two sources of information. And in particular, because model output can be quite big, we want to actually summarize them with some statistics. And I tend to like to view all of those two sources of data as a proxy to an underlying like true physical process. And so when you think of like model data, for instance, typically you get a grid. This is a coarse resolution, for instance. This is a much finer one. Let me try to see if I can collapse. I need to try to collapse here. Yeah, there you go. This is a much finer resolution, and the black dots here are actually measurements data. So you can think in terms of statistics and information, you're gonna really extract different information from those different sources of data. And so, like I said, typically model output, and especially nowadays, they are running at extremely fine resolution. So it's a lot of data. It's very difficult to just sometimes move and load them. So our idea here is what was to work with lower dimensional representation of them, and then enhance them with observations, and hopefully output something that is on the grid of the model output, but that is informed by the observations. Okay. And so when we think about summary statistics, right, some of the most common ones are the one we learn in our first actually statistics class, like mean, median, variance, but that is not super informative. I mean, it is on the first at first glance. And then we also have the more classical, also dimension reduction techniques. They are mostly based on linear assumptions like PCA, EOF. EOF is empirical orthogonal function. That's the space-time extension of PCA, basically. And then there's also the new class of machine learning based basically encoders. Those are very powerful, but they are quite black box here. We don't really know what we learn in the latent space, for instance, as well. So yeah, here we had really a big trade-off between how much we lose of information, how much we keep, and also the computational complexity. So if you go towards an autoencoder, for instance, you're gonna have to train it. So that's also something that you want to keep in mind. So what we decided to do actually is what Atlanta, what was really interesting is Atlanta has this background in approximation Bayesian computation, and past signatures have been used actually for ABCs in time series context. So we decided, all right, let's try it. So what the past signature does, it actually takes a time series and creates a collection of iterated integrals also on various windows. And then you can also tune up the degrees actually of interaction in your integrals between the multiple time series that you have. And it turns out to be used in many fields, very powerful actually to summarize what happens in a time series. So you can learn the entire displacement, the area. Those are the first order under the curves. Those are the first order statistics. And then you can achieve more complexity in when you increase orders in this method. And so that's what we picked as a method actually to summarize our physics-based model output. And so our idea was to input those summary statistics into a network, a neural network, and try to reconstruct actually this state, but also inform it with observations. And what we had, because the observations are sparse, as you saw on the map earlier, what we also had to do was to input actually the neural network with deep Kriging basis function. So the idea was to input those basis functions that are going to help learn local information around each observation station to like spread the information that we know about the observations in their neighborhood. So our training was performed with those summary statistics of model output, those deep Kriging basis function, and outputting some of the observations station that we know. And then the end goal was that can we actually later on interpolate on the entire grid this output, and that is really done through the help of the Kriging. So let me show you the data that we've been working with. It's a different data set than I showed earlier. We applied this method to a temperature data set, like surface temperature in the upper Midwest. The data set, so the model output is coming from this NLDAS reanalysis data. It comes at an hourly temporal resolution, and it covers that area. Actually, it covers at least the entire US, at 12 kilometers grid. And so just that area actually is 5,000 points already. And then as we discussed, right, we also want to have some observational data set to complement that this model output. And so we extracted NOAA LCD, so it's NOAA local climatology data. And in that area, we could get actually 213 observations. So that's quite a good amount actually here. It's not always that you can get so many measurements. And here I'm just showing the mean of the temperature and the standard deviation. So yeah, you can definitely some spatial pattern that arises from having access to the grid, right? It's much easier to visualize. You have more complete information. And then if you look at what you get though from the measurements data, you can also see that the measurements data here, the intensity here of the standard deviation, but that is also true for the mean, is very different locally from the sort of like coarser scale that you get from the model output. So really our goal was to leverage like both sources of information, like the large scale that you can learn from the model output and then the localized information from the measurements. And so I wanted to show you what are the path signatures looking like. So here, the way we proceed, so we take our model output data, we compute the path signature at every grid point. So that is not actually cheap, and that's what we're working on now, actually, to alleviate that step. But as a first iteration, that's what we did. And then we performed the PCA actually on all of those path signatures, and we try to catch the main modes of variability. And so we call this two-step SIG PCA, sorry. And this is what some of the summary statistics are looking like. This is for the entire year, for instance, of data. And then we looked at smaller windows also. And so this is looking at the global window, and this is like narrowing down here towards like smaller windows. And there's various things that we can see. So here I'm plotting 5 of the most contributing location out of that method from the PCA extraction. So we can see that the SIG PCA, we're able to extract actually that seasonal pattern that we see on the temperature. So that was very neat. And then when you start to look at smaller windows where you kind of get like finer grain information, also what we were quite happy to see is that we can capture different information from different stations. So it seems like this path signature is really capturing a lot of the temporal and spatial patterns of the data and really also the diversity of it. Yeah, I guess here I just wanted to show quickly where are those 5 locations that were the most contributing. So it seemed like they are kind of spread into areas where we may, for instance, here by the lake, we may have also, for instance, a lot of variability here. So so yeah, it turned out we saw a bunch of points on the border of the domain. So I think this is something we need to think a bit what's going on there. But what I wanted to show also is really those stations, they tend to have the same trends in the way they contribute to the different way of assessing the different scales, but they do contribute with different intensities also. So they really carry different information. Okay, so then let me tell you how we proceed here, just to recap. So we have those core scale basically model output data, the observations, and so we trained this network actually with the summary statistics. We added the deep kriging basis function, so we can do some spatial interpolation, and to actually be able to really carry that, we also fed the network with latitude and longitude coordinates. And the idea was to output something that is like the observations. And so we did that actually in 2 steps. We broke it in 2 steps. The first step was actually, can we only recover, and that was also a way to test our method, can we only recover the model data? So you input your model data, summary statistics, latitude and longitude, and deep Kriging basis. Can you at least recover what you have just been compressing here? And then the second step was actually, now that we've recovered that model data, let's learn actually the discrepancy between those model data and the observation. So here we also output the model data at only a reduced percentage of the grid points. We don't do all of this neural net training on the entire grid, which is really helpful. Also in the neural net training, we have a much smaller neural net, much smaller training. Yeah, so I guess that's something I should have said earlier, is like, most of the work, when people want to correct model data, they're actually going to build a model that is going to be fed with the entire grid of model data, which can just become really cumbersome, especially now when really data size is exploding. And so, yeah, so at least just recovering the model was working fairly well. I'm going to show some results. And then we added this correction step where we learn the discrepancy between the reconstructed data and the observations. And then the last step was actually to put this together in just an additive fashion. And then the output that we get actually is a reconstructed model corrected actually by the observations. And so as a benchmark also, we wanted to benchmark this method, right? Just to really make sure that the path signature was also, I mean, it's been trusted in the area, but I had not seen it much actually in the atmospheric science field. So we wanted to test it against empirical orthogonal function, which those have been really used extensively in atmospheric applications. And so we constructed this empirical orthogonal function. So basically what it does is like you do a PCA in the spatial dimension, and then after you project your field on those eigen vectors, and the weights, the loadings are actually time series here because we are working with the space-time fields. And so you can reconstruct your field like that by really separating spatial and temporal basis. And so we use those actually as a summary statistics of the reconstruction and corrective model, right? So basically here, instead of inputting the path signature, we input a reduced set of the empirical orthogonal function. Okay, and so this is what the mean temperature looks like. So when we reconstruct the field, we can we really have like an entire space-time field. And the spatial extent is really the spatial grid, and then the time steps are all of these time steps also from the model. So this is the mean of the temperature from the model. The circles are the observations data. They are not used yet here. This is how we can recover actually the temperature and the mean of the temperature when we do not use observation, but we just use our method to basically like compress and decompress the model data. So that was really our like kind of critical validation. Like we really we know what's the ground truth. Here it's this. So if we do not perform well here, then it's really difficult to go further. So, but we were quite happy. I forgot, I wanted to add the numbers of the errors here, but the relative error is very decent here. But then if you see, we're still missing in this reconstructed model, for instance, if you look at local observations here, you have a big mismatch in terms of intensity. So then this is why we added this component of correction with the observations. And this is the field that has been first reconstructed only and then corrected. And what you can see, actually, you can see those little halos around the observation station. So now you can see that this gridded now output is a little bit closer actually to the dots. So it means that this field that we have corrected is indeed coming closer to the measurements. And then basically the halos is really the kriging, right? Having this kind of range of action that helps spread the correction. And then when the correlation dies, then the correction kind of vanishes as well. But so we were quite happy actually with those, and we can capture, and sometimes we have a few artifacts, like here it happens, but overall, like the discrepancy between really the gridded field and those dots, we found that is much lower after our method. And so the comparison, when instead of inputting past signature as summary statistics, we input the empirical orthogonal function. This is what we get when we want to recover the model data only, and this is the correction. So the correction is a little bit better, but still you have this huge artifact that we were still like puzzled like how this can come. But we saw it also on another data set that really when we do not, when we use the EOF as a summary statistics, we were really struggling to get back actually to the model. So that's was interesting. Like you need to go beyond like a linear summary statistics also to catch most aspects of the field. And so I just wanted to show further validation. So that we looked at the spatial aspect, and now I wanted to show you some time series. I'm showing you the location 2. I forgot where it is exactly, but basically we picked it because it showed, yeah, it's here in the center. We picked it because it had, it looked like the error for this location was low in winter. Oh, I think my colors are not showing here. At least not on my screen, sorry. But at least that station had low error in winter, but high error in summer and fall. And so then here I wanted to show what it is like when it's behaving well and when it's not behaving well. So basically our goal is we would like really the red curve to match actually the blue curve. So the blue curve is the observation and the red is the reconstructed model plus its observation correction. We were fairly happy, like we can actually, for instance, help those peaks, like capture them better than if we were looking at the model only, which is the darker green. So we were able, for instance, to boost actually those peaks in temperature. We were quite happy. And then what happens when things are not going too well is what we can see here. It's not too dramatic, but somehow we're just not doing as well. We tend to overestimate a bit and underestimate as well. So that was what we could see. But overall, the errors were fairly so yeah, we're fairly good. I wanted to show this, but those here are supposed to be box plots, and they represent the improvement of RMSC when you use the correction data that we build, as opposed to if we were using actually the pure model data and trying to approximate the observation. So the higher number here means that you are just doing much better than the original model data to capture the observation. So if you can see at least the box plot are lying here, which are fairly good percentage of improvement. Okay, and then we also, let me check what time is it. So to validate further, we wanted to see how much of the distribution, the probability distribution, are we catching well or not so well, and when. So we split the data again in season. Here, each season is a column. And then we evaluated, basically it's a quantile plot, and we wanted to check those 3 models that we built, how much do they recover the quantile of the observations. This is if we apply our model, we feed the neural net with summary statistics of the model and just try to output the plain observations. It does quite well. This is what happens if you just reconstruct the model data only and do not apply any observation. So it's okay, but not as good as the other one. And then here really the best fitting in order to fit the observation quantiles was really to reconstruct the model data first and then apply the observation-based correction. And each season we were doing fairly well, although some season had a little bit more spread. And so final validation I wanted to show was the spatial correlations. So here we are showing the spatial correlation as a function of the distance between the grid points. The gray dots are actually the spatial correlation of our observation stations. Each row is a season, so we can really see the spatial correlations have seasonality, and which is expected because really the variabilities of the field change. And then here in blue is just the original model data, no correction. So you can see already the blue and the gray are not matching. The model data actually tend to overestimate the observation correlation, the observed correlation. In this column in green is the sort of our best setting when we reconstruct the model, but also use observations to correct it. And this is where we match the observations in gray the best. And we are even able to catch the seasonality also in the correlations. And those, this is what happened if we reconstruct the model only, but not use observations. And this is what happened if we try to output observations only, and actually we don't match as well the observations. And that is what we found really interesting here, is that basically if you want, because we are sending, I guess, everything into a neural net model or a model, you actually need in order to recover best the observation, you still need to use actually the model summary statistics. Otherwise, you tend to lose actually or distort actually the correlation fields. And I guess it's because you are passing everything into a neural net. So I found that very interesting. Okay, so that's everything I wanted to show on that topic. So yeah, the idea was to build a neural net to that could kind of merge together some summary statistics of a graded model, enhance it with observations. We were quite happy with those summary statistics because we could get a lot of interpretation out of it. And we also work with wind speed, surface wind speed. That was more challenging actually, because in that case, we had the ratio of observation station to gridded model data actually was much lower. We had much fewer weather station data, and also wind speeds are very localized. The space-time correlation, they just vanishes really quickly. So it's much harder to recover, but still though, it was doing fairly okay, just not as good as temperature. And yeah, our next big step now is, can we bypass having to compute this path signature at every grid point? So if we want to scale on a much larger area, we would really want to think smartly how to do that. Okay, so maybe do you have some quick questions? I wanted to show a bit the other topics, or do I keep the question maybe for the end? I know that you're talking, but I don't hear, but maybe I just keep going.
Yeah,
Sorry.
like if there are any quick questions, we can have them right now.
Yeah, exactly.
Oh,
I have a question, Julie, about how frequently were the sample observations taken? And at what time of day?
Yeah, exactly. So originally, actually, the data set is very rich. It's collected every 5 minutes, but we only worked with the hourly one. Yeah, there was a so it was rich because it was collected every 5 minutes, but it had a big drawback. It was actually recorded in knots, so they rounded into an integer. The measurements, that was quite tough. So what we did a little filtering over, I think, 1 hour window to try to get things less discrete, but then we lost maybe a bit of information again there. But yeah, we did work though. At the end, we worked with 1 hour data, hourly data.
I have a quick question. So for the summary statistics, are there like rigorous like error bounds, like if you're using that summarized information?
That's a good question, actually. We need to check that.
Okay.
Yeah, if there are any, it is extent Atlanta, maybe. I don't know if you, I don't think I've not come through it actually, but it's widely used, but it's a good point.
We don't really have error bounds as of now yet.
Yeah, right. Yeah. Mhm.
Like in case of any like sort of rare events or something like that, how do these summary statistics vary? Like if there's a earthquake and thing like that, like how does the model perform in those scenarios?
Yeah. So because I mean, right now we calculate them at every grid point, right? So at least you get some spatial, very local information that we want to move away from that, but at least we get that. And in time, we like zoom in also, right? We start with looking at a large window and like slowly look at smaller windows in time. So you do see though a lot going on, right, across time. So for instance, we don't see an earthquake. I mean, well, we don't have earthquake there. I don't know how that would manifest, but um, the fact that you can see actually here's an entire year of data, and like here we can see like the entire season, right? This is the summer. You can see that the summary statistics is catching that. So it does capture this non-stationarity. So I would imagine whatever data you would look at, if there is like an earthquake which is a non-stationarity, I don't want to say that we would catch it, right? But like at least it seems to capture some non-stationarity to some extent. Yeah. And it does also, sorry, even also different location like gives us different path signature here, right? So it has captured also some spatial variability as well. Sorry, I think somebody had a question.
So Julie, this is a lot like just fluid dynamics, I guess. And you're looking at motion.
Yeah.
And
Yeah.
my supposition is that temperature has a massive impact on wind speed or,
Yeah.
motion. So is there any correlation between a much more relevant variable than an earthquake, but temperature? Because San Diego doesn't vary a lot in temperature, but in summertime it gets hotter in the day, and that's going to in fact make the wind variability greater.
Yeah.
There's nothing like here with the temperature variabilities.
Yeah, I think I see what you mean. I mean, I'm not sure I'm not sure if I understand the precise question, but yeah, I mean, definitely so wind speed is like very strongly tied to temperature, right? Like yeah, totally. We have not thought yet actually also of extending our framework to two variables, but definitely we should. And I think actually those path signatures also are they are pretty good at capturing like multivariate time series. So yeah, it's just the wind speed we work with there is a different data set. Also, this is why they are not correlated. It's a different data set at a different time, different area even. So but it's a good point. Yeah, we could try to do this multivariate thing. Yeah. Do you want me to show the second work? I can go quickly if you don't
Yeah.
have more questions. Okay, so that is a work that I started a long time ago with a student Daniel Getter, he was a student at Oregon actually with me for 2 years, but then he left to grad school and could not finish. And so now we are working with it with Harrison Goldwyn at NREL, Johan Rudi at Virginia Tech, and Mitchell Kroc at the University of Missouri. And so we are about to be done now, and we are writing a paper. So the idea was that we wanted to leverage the sort of old-fashioned, I like them, so I don't want to be mean, but the more classical neural networks. But we were not very happy with the fact that you only get a deterministic output out of them. So we wanted to equip them with some sampling capabilities and maybe a closed form probability distribution. We wanted to avoid going to generative model just because their training is prohibitive, and by experience we've struggled a lot. I know some people really love them, but we've struggled a lot, actually, all of us, with them. So like I said, when you have like a classical neural network model, so you have some input, some output, but the output is completely deterministic. And so instead, what we were hoping, can we actually build a distribution for this output? And so to be more precise, also, when we apply that to Superresolution, we have some input that are coarse resolution data, some target high resolution data. And could we learn the distribution of those super resolved data that comes out as an output? And so a sort of first thing we wanted to think of is a Gaussian distribution, and I'll discuss also the limitation of that assumption. But yeah, could we get a mean, which is basically the super resolved field, but also a covariance of those fields, so that we can, if we choose to use the Gaussian distribution, then we characterize fully the distribution here. And so to see how we could write that, when you train a more traditional neural network with the classical mean square error loss, your loss would write like this. Y is your observation, and mu is your target, in our case, like super resolved field. And so how about now we try, and so this came also to our mind because we are really working with spatial fields here. And when you use the classical MSC here, you're just really not accounting for the correlation between points when you sum up your mean square error loss here. So the idea was like, can we move away also from this inner product and have like a more informed inner product? And I mean, the idea was that we could do that if we try to fit a Gaussian loss, and it would write like this, right? So conditional on the data, can we output the mean, which is the super resolved field, and the companion covariance? And it's very easy to write it like that. The idea is very simple, but it was really hard to implement. Maybe I can show you, let's see. Yeah, I can show you quickly how we did it. So we had to split that in 3 stages. The first is that we do a traditional mean square error loss. We get a super resolved field that is our mean. Then we did a maximum likelihood only step where we estimate the covariance actually associated with the error that we get from stage 1. So here we have, given the observation, given the output, the super resolved mean from stage 1, we get a covariance here. And then what we did in stage 3 then is plug everything back together and then use that covariance into a loss here, into that loss. And that loss is really the one that we train the super resolution network again with. And so basically the outcome here, so is like an it's coming very close to having the distribution of the super resolved mean, its covariance given the data. And so it was still pretty challenging, even broken into those 3 steps. We had actually to expand the field into Fourier basis. so that we would have fewer parameters to estimate, right? So in the covariance, so instead of having this fully populated covariance, we only estimate the diagonal that consists of the variance of the Fourier coefficients. So that was one step to make everything lighter and more stable. And then the second step, we had to regularize still those diagonal like Fourier coefficient variance. We had also to regularize them to make everything more stable. And then once we had done all of that, we could plug everything back into the third stage, where really we use that loss as the loss of the neural net that does another step of super resolution. And just to show you, for instance, to illustrate how much numerical instability we had, here I'm showing the regularization as a function of the regularization weight. What is the quality of the predicted super resolved output? And so we kind of like do very stable here, and then suddenly when the regularization is too weak, we just completely break, right? But like here, you imagine you go from 10 to 5 and it doesn't move too much, but then here it becomes very sensitive. I mean, we have also an inverse, right? So we have to be careful, but everything just degrades really fast, and we just tend to see those very extreme like numerical behavior a lot. Here is just showing the mean absolute percentage error actually of the super resolved prediction for those different scaling factors. And so very quickly you see we do very bad. And here is interestingly, this is actually the error in the gradient. So we take the super resolved image, calculate the gradient, and then calculate the error between the original gradient and the predicted one. And what I wanted to quickly highlight also is we are under the line 0, meaning that actually our method was kind of always doing better than an MSC model. So at least we were also happy that now we are building these sampling capabilities, but we're also doing slightly better than the MSC model. So, okay, now I just want to show you quickly what our samples looking like. This is the low resolution input. This is the target image. So the upscaling factor is quite big. It's a fairly challenging step. And this is the mean prediction, like the super resolved mean field. And those are actually samples that we can get now when we use our mean, and also this outputted covariance that we have. And if we plug it into a multivariate spatial Gaussian distribution, then those are the samples that we get. So we were quite happy that, yeah, this works. It was actually quite hard. I know to the eyes, this is not actually that exciting, but I want to show you then a surface box plot. So surface and functional box plot, they are the analogous of a classical box plot, but for functional data. And the idea was that there is a metric called band depth, and it measures the centrality of a curve into an envelope of curve. And those functional box plots have been built on those. And basically, you can calculate quantiles like curves. And so those quantile curves are curves that have been ordered via this band depth measure, right? And so the most central curve is going to be the median curve. And then you can then create like outliers curves. And so here is what those functional box plot looks like if you slice up this surface box plot. In green is the target slice also that we try to recover. And so we can see that most of the time our samples are covering actually the target slice, which we were quite happy as well. And here we can see a bit of more of the variability also that tend to not show with the other color scale. And just super quickly, one last slide. We tested also two setups. One setup is having a covariance that is global to the entire training set. And we tend to be a little bit overconfident out. And we do not cover as well actually the target image. And instead, because we know that also our data set is actually covering the entire Indian Ocean, so we know that we have spatial variability, and we just have a bunch of small images covering the area that we wanted to try an image-specific covariance, which we could do because we have this projection onto the Fourier basis. And so we were able to have a bit of less confidence, but somehow also the mean of our samples is coming a bit closer to the true target image. All right, so I think that's my last slide. So thanks very much. And I wanted to also acknowledge the funding sources. So this work is funded by the US Department of Energy, and those are parts of two different projects, two different fundings. So the first one was the Early Career Program of the Office of Science, and this one was the Energy Earthshot Initiative, also part of the Office of Science. All right, thanks very much.
We can open it up now to questions from the floor. I had a few quick questions.
Yeah.
So the first one is related to some of the deep rigging stuff that you showed in the first part of the talk.
Yeah,
So
yeah.
I was wondering, like, what is the main advantage of doing deep kriging versus regular kriging? So is it related to capturing some of the trend of the error better in some regions, or is it more to do with how the data is, like its stationarity, and then maybe capturing that through the covariance somehow?
Yeah, exactly. So somehow this deep, I mean, it's called deep kriging, but
Okay.
it's called deep kriging, but you don't really do this like covariance like product and inversion that you do in kriging, right? So then you can free yourself from this non-stationarity assumption. That was quite nice also because our areas are clearly non-stationary. So yeah, like you said, yeah, the non-stationary was a big issue. And then it's just having that as an input of those functions, those spatial function as an input of the neural networks was really, really more flexible.
Understood.
And somehow also it's still expensive to train a network, but like doing kriging on this giant grid, the classical kriging, and we could not afford, right, to do the classical kriging on that giant grid. We would have need to sort of breaking down, like the covariance would have been like 5,000 by 5,000. So
That's right.
we would have had lots of problems.
And then the second question is like, if you had like n grid points and let's say a certain time resolution, what is the general computational complexity of getting these rough path signatures
Yeah.
in worst case
Yeah.
scenario?
Do you remember Atlanta? I think we talked about it, but I completely blank out.
Every window, it's a constant. You're just computing the differences between the end point and the starting point. So what really matters is the number of windows you're really considering. So it's just constant for every window, and the further the number of windows, it's that computational factor.
Thanks. Questions from other people on Zoom? Feel free to unmute yourselves or even type in the chat.
Hi, I had a quick question. My name's Ray. I had a quick question about the first part of your talk. I really liked it. I was just wondering if you saw maybe any utility in using like the summary statistics framework and applying it to data from like, let's say, biological samples. So I'm like thinking about like spatial positions of cells and like corresponding features there. Do you see any sort of like utility in that framework to maybe like predict or classify or do any sort of like analysis on samples like that?
Oh, so you mean that your data this time, the sort of output is a position? Is it what you mean?
Yeah, exactly. Like I'm thinking of like a tumor sample. So instead of like a map of the United States, I'm looking at a map of cells and I want to learn some information about the patterning there.
So I don't know exactly about your data, but I mean, they have been used in many fields actually, those past signatures. So I could imagine that you could, yeah. I mean, basically, as long as you could like write like the mathematical, so they are not also limited to time series, right? As long as you could write things into a mathematical object that fits, like people have used them in clustering, definitely, and extracting features.
Okay, cool. Thank you. Thank you.
Yeah, and maybe Atlanta actually can also tell you more because she has worked with those like much more than me also in the past.
Yeah, I think it's a domain agnostic framework, so it's pretty easily extendable to any sort of application. But of course, it comes with its own caveats that you might have to modify the basic formulation of it, maybe. Yeah, but in general, you can apply it.
Okay, cool. Thank you very much.
Okay.
Thanks very
So
much.
yeah, let's thank our speaker again for this wonderful talk. And
Thank you so much.
All right.
and,
Yeah, great.
we'll see you all again for the next seminar in a few weeks' time. Thanks everyone for tuning in and participating.
Thanks.
Thanks so much. Bye bye. Nice to meet you.